So welcome. This is my talk on basically I'll be going over some of the things that we've encountered over the years at message systems. So before I go into a bit more about what that means, I want to get a feel for like who you guys are and the kind of things that you're doing. So how many of you are developers? Can you, hands raised, like a good chunk of you? Okay. How many of you guys are operations guys? A fair chunk. So, and just for the sake of it, how many of you are DevOps? Oh, that's interesting actually. So less of you class yourself as DevOps than there are ops guys. So it just seemed like there were a lot of folks that did, from the hands that went up, a lot of the folks that said they did dev also seemed to have ops hands go up, but they didn't call themselves DevOps, right? So just interesting, because it's not the same thing. I don't know. So anyway, I'm just curious. So of those of you that do development, how many of you develop in the one true language, C? Damn. All right. How many of you are using Node? Okay. Ruby? Python? It's like a real mix. What else are people doing these days? Perl. How many of you do Perl? That's actually a lot more than I expected. And so of those of you that are doing Perl, is that because you're doing like back-end job stuff because it's sort of more opsy, or is that like apps? Okay, very very interesting. So we've got like a good mix of folks in the crowd here today. I'm mostly a C guy. But I'm not religiously a C guy. I go up and down on all over the place in the stack. So a lot of our experiences or that I'm recounting are based around the things that we've had with our Momentum product, and so I didn't really want to do a talk where I go on about how message systems is awesome and we've got all these awesome things, but I kind of have to set the scene a little bit to give you some context. So this is one where the marketing folks will probably be quite happy, but I view it as like a necessity to give you the context. So. Oh, actually, I should have asked, how many of you are actually message systems customers today, just to get a feel? Okay, some of you. Cool. Good. I'm not trying to sell out the rest of you on our stuff. I just want to give you some war stories kind of thing. So Momentum is our flagship product. You can think of Momentum as being something like the Apache of an SMTP server kind of world. That's like a really, really gross injustice to what it is and what it does. Like, it's actually nothing like Apache. So anyway, it's a modular, high-performing server infrastructure platform. This is all sounding really buzzwordy. But the idea is that our customers need to take in, on one side, a whole bunch of messages and do some stuff in the middle, and on the other side, send out a whole bunch of messages. And that's what we're really focused on. So we have some big name customers that you've probably heard of. So folks like Facebook and Zynga, Match.com, Salesforce, Digital River. So how many of you remember a little while ago there was this big brouhaha where somebody's database of email had been compromised, and then you got these emails from people that you'd never heard of saying, "We're sorry, our database got compromised." That's not our fault, by the way. Just want to make that clear. Sorry, some of those folks are some of our customers. So what they do is they provide email services on the behalf of other people that you do business with. So people like Best Buy and TiVo. Like, I actually got emails from these folks too. I was like, oh, cool, look, they sent that through our product. But I was like, shame it's not like a happier email. But anyway, they send a large amount of email on behalf of a large amount of people. So there's a lot of sending going on there. We also do some stuff on the receiving side, and this is where I sort of go into a slightly cop-out kind of a thing. Not many of our receiving customers like us to talk about who they are. So there's only one that I can really call out here, and that's a company called Message Labs, and they provide email filtration services. So like you point your MX at them, they do all the crazy policy, anti-spam, antivirus stuff, and then they go route that back to your actual inbox servers. So they were bought by Symantec recently, so you may have heard of them as Symantec.cloud. So there's a lot of folks doing a lot of interesting things with email on our platform. It's not actually just email. So we started shipping SMS and MMS protocols as well. So you inject messages into the system, and we make an intelligent decision about where that goes. So that sort of gives you a bit of background. We provide a software product that you go and deploy on your own hardware. So actually, that's one of the questions I should have asked. How many of you guys operate a service, and how many? So if you could, you have like some kind of a service app thing that you do. Okay, and then how many of you guys actually ship a product that somebody else operates, where you don't have access to the hardware? Okay, and there were some folks in the middle that didn't have hands either way. So most of you guys actually operate the stuff that you have. For us, it's a bit difficult because we're a software vendor. We're probably the guy that you hate. Or at least not message systems. Software vendors you tend to hate because things don't work right, generally speaking. Let me rephrase that. When things don't work right, you blame the software vendor or the hardware vendor or whatever. So like I have that sort of slightly uncomfortable position up here in front of like a more of an operations focused thing. But so anyway, that gives us some challenges because our developers don't often get to be directly on the systems that are operating. So we have that sort of barrier to getting hands on there. So it's just like an interesting difference, I think, in mindset. So that's the sort of the sort of slightly marketing type part of that marketing didn't ask me to put in, but I felt was necessary context. So I want to get onto some fundamentals. So on the summary for this talk, when I proposed it, I can't remember exactly what I said, but it was along the lines of it's challenging to build like a really well architected system. And even when you think you've done a really good job, there are some unexpected things that can happen that can come and bite you and really ruin your day. And those failure modes are perhaps more acute and painful than they would have been if you had maybe a more naive architecture, because you were trying to be too clever, perhaps. So anyway, some fundamentals. Our architecture choice is an evented I/O model. How many of you have read the C10K thing that I've got up on the slide here? You know what I'm talking about? Okay, so for those of you that haven't, there's this webpage. It's been around for a while. Like if you can easily Google for it and find it. But this guy Dan Cagle, he had a particular interest in trying to scale his services up so they could handle more load. So he has a question, why can't Johnny serve 10,000 clients? So he actually has some really interesting analysis in there, contrasting things like, if I use this sort of event-based thing, I get this sort of throughput. If I use a threaded model, I get this sort of throughput. And there's quite a lot of interesting discussion there. Now, the data on there is actually a few years old, but the concepts are still really applicable. So the C10K thing seems to indicate that the evented model is pretty cool. And it's not just Dan, it's not just us that think so. The Node.js thing is an evented model too. So it seems like a good idea, and it really has worked out well for us. But we're not purely evented. We use a series of thread pools that we allow the operations guys to go provision, and you have a certain degree of control over, I want this thing to run in this thread pool. And we have some predefined pools for certain tasks, and I can go into that a bit more later on. But we operate on the concept of there being a single scheduler thread that basically sits there using ePOL or portfs to listen for when things are ready to go on the network, and then just go do that. And most of the time it's like, I want to read something out of this buffer, and can I advance to the next state in my state machine, and then wait for the next thing to happen. So we can get quite a good clip through that architecture. Similar to Node, very sensitive to things that block on the scheduler thread. But our solution is, well, we just go kick off a job to an appropriate thread pool, and we're golden. So, and some numbers there. We advertise, and we have done for a long time, the ability to handle up to 100,000 concurrent sessions and do 1 million messages an hour throughput on commodity hardware. Now, we've actually said that for a long time. in theory, you can get higher than that. And actually, in practice, I was talking to one of our customers the other day. They're getting like 3 million easy on one of their systems. So, but you can go much higher. We can get to double-digit millions in the lab. The thing is, the lab isn't the real world, and there's all this deliverability stuff you need to worry about on the other side. So like the raw capacity of the system is quite high, which is cool. We think it's awesome. So we've got this really cool framework. You can think of it as being a bit like libevent on steroids. We started building it before libevent came out. And so anyway, we have this framework, and our services are built on this framework, and it's a solid foundation, and we can do some really cool things with it. One of the challenges, though, is most of our customers deal with SMTP, and SMTP was designed in a different age. So I've looked into this a few times, and I was trying to find, like, what was the earliest trace of SMTP that I could find? There's actually an earlier trace than this, but I looked all the way back to RFC 772, which you've probably never heard of, when it was actually called MTP, Mail Transport Protocol. So at some point after that, it became the Simple Mail Transfer Protocol. So anyway, that first showed up on the internet in the 1980s, and I realized that's how old He-Man is. And not that I'm a He-Man fan per se, but my son, he's totally into He-Man now. So I just thought it was an interesting thing. So it was born of an age where we were much more trusting, and we would have like a little moral segment at the end of our cartoons to sort of say, like, bad things are bad and you should be good. So it's a little different from today, where there's all these people out there just trying to DOS your service. So there's some fun parts of SMTP that make it challenging to build a high-performing system, because the protocol kind of gets in the way a bit there. So, it's a line-based protocol. It's really chatty. It's, you connect, wait for the banner, then you have to say hello, and then you can say, well, I'm sending a mail from this person, and the other side says, okay. And then you can say, well, this is who it's going to, and it's like, oh, okay. And then you can send the data, and then at the end you have to put crlf.clrf. And then the other side has to go write that to disk and guarantee that it's stored on disk before it says OK. So there's like it's difficult to get like a high rate of these things through, just because of the round trips and the high latency on there. Not much you can do about that, because that's the protocol, and that's the one everyone speaks. So anyway, so there's another little bit of context in there for you. So moving on, I mentioned that calling it just an SMTP server is like a great injustice, because as it turns out, nobody really wants just a mail server where you put mail in one side and it goes out the other. You actually want to do something in the middle, right? So the types of things that our customers want us to do with those systems are what we call policy, right? Which is like a big catch-all for, like, I want to do my business logic in there, and my business logic can vary as you move between those sort of different areas that our customers move in. So on the receiving side, I want to make sure my policy is that I don't want to receive mail from people that are on blacklists, like they're known spammers. We just don't want them, right? If we can look up their IP and turn them away, we want to get rid of those. So we have RBLs for that. And then by extension, I don't want to receive any kind of virus mail or spam mail or porno mail. I would like to try and eliminate phishing mail too, right? So like I don't really want to relay messages that are gonna go compromise somebody's Citibank email, Citibank bank credentials, or actually want to make sure that the mail that's coming into my system is from people. It's really from the person that they claim to be. So I want to do some digital signature verification for folks that have taken the time to go sign their mail with domain keys or domain keys identified mail. So that's sort of the receiving side. Those seem pretty obvious cases. On the outgoing side, as a responsible sender, we want to make sure that we're following all the best practices. We don't want to send too fast. We want to make sure that that we sign the mail that we're sending, so people can make those determinations. And so those are just sort of like the meat and potatoes of sending messages. You want to make sure you're doing it right, doing right by the people that are going to receive it, and on the receiving side, you want to make sure you don't allow any crap in. But then you have some more interesting cases, which is when you start coming up more to the actual business logic. Because I think to a large extent, this content scanning and traffic shaping and signing and so on, though, you just have to do those. Those are like a cost of doing business. So what's more interesting is when you start going into doing things like, well, you know what? I actually have this guy's cell phone number on file, and I know their preference is that when they get a particular type of message, instead of sending them an email, or maybe in addition to sending an email, I want to go send them an SMS as well, because maybe it's a high priority thing. Or for this audience, this ties into my default example for this. When an escalation comes in to my email address, wouldn't it be cool if the email server could say, oh, they're on call, I'll send them a text and send the email to them. Or even better, because we're starting to move into instant messaging as well, they're online on Jabber, I'll send them a Jabber message and an email, and then I don't have to go send them a text or whatever. So there's some more interesting cases beyond that, or even just gluing things into other systems. So I was talking to Gavin from the Rabbit MQ talk earlier, and he's doing all kinds of stuff where he throws things into Rabbit and has all kinds of clever, what's the word for it? There's all kinds of like a triggering logic in there to figure out whether he should then go send things out over email or go do some stuff in his back-end architecture. So just based on messages flowing through the system, it doesn't even have to result in another send or something. It just can be tying data back into other systems. So there's a lot of stuff that our customers want to do on top of our platform. So we can build a system that can send email like nobody's business. But when you start throwing in the ability for customers to go put some scripts in there, that actually poses some challenges. Because how do you enable, it's a challenge to build a system that goes fast. If you're the person building it, you know what you need to do to make it go fast. But when you put it in the hands of other people that don't necessarily know how to make those things go fast, how can you make it so they can go extend it and do the things they want to do and still make it go fast? Right. So that's some of the challenges that we have. So there's a lot of background there, and so I'm going to move into the sort of start of the lessons that we've learned, right? So this one I'm sure is a no-brainer really. Disks are a fundamental bottleneck when you're trying to put mail through a system. Who knew? So so we have like triple-digit hundreds of messages transiting the system. Those need to go to spool, and because of SMTP, we have to sync those to disk before we can say that we've taken delivery of those. So that's a good deal of IOPS going on there. In addition to the messages going on, we also want logs, right? Because you want to know what happened, right? So we have depending on what happened to the message, typically 2 to 3 log lines. You have like a reception line and a delivery line if it came in and went straight out. Maybe there was a transient failure, so we have like an extra log. Maybe it's has a persistent deliverability problem, so we have a whole series of transient failures for that message before we either successfully deliver or give up. So yeah, disks are like the obvious first thing in there. So as it happens, there are some pretty obvious things you can do to mitigate that, right? So get it provisioned properly, right? So you put your spool on a separate set of spindles from your logs, maybe separate set of spindles from the OS, have some good fast disks, no A time, that sort of thing, right? So I probably don't need to tell most of you about how to do that. So like that's just like, let's get the system in a good shape for that first of all. But that doesn't solve all the problems. So what we do is we want to manage more effectively how our messages hit those disks. And so what we do is we use our thread pool model for that. So we have a handful of predefined thread pools. So they handle like various logical phases of mail in the system. So on the typical reception path, we'll have messages come in and we'll want to write them to disk. So we'll actually do that disk I/O in a swap out pool, and you size that to amortize the cost, because those things are going to be blocked, waiting for your spindles to take the data and put that on the platters down there. So you can control how many of those you've got going, and that can help you manage the load that you're putting on to that disk subsystem. On the flip side of that too, sometimes we'll want to read messages back in from the disk, so we can control how much load we're putting in there for that as well, because we'll just have the swap-in thread pool manager. So you set how many threads are in those pools. So that lets you manage that stuff. And also unlinks, right? Because when you're done delivering a message, you don't want it on your disk anymore, so you have to unlink it. An unlink is like a little innocuous call. Yeah, I've unlinked it, but actually it can block. So you don't want to do that in the wrong place. Actually, unlink is kind of a fun one, because you need to unlink it so that if power is interrupted and you come back up, you don't deliver it again after you've had that power interruption. So you want your unlinks to go immediately, but you don't want to block, right? So we have this challenge. So we have this unlink pool where we just queue up a whole bunch of unlink operations, but it's quite easy to go have like hundreds of thousands of events backed up waiting for your disk. If you have some kind of a problem with that, that's not a happy situation to be in, because if you do lose power at that point, you've actually delivered maybe 100,000 messages, and when you come back up, you're going to go deliver them again. And from an email perspective, that's really bad form, because if you're sending a lot of mail and then you end up sending a lot of duplicate mail, that sure looks like spam, right? That's not good for you. So what we do is we set a backlog, so we set a maximum queue length on that unlinked pool to act as a safety measure for that. So those thread pools allow us a good bit of control over our disk usage there, which is essential, but it's also very effective. One of the other things that we noted, and this comes back to like the making things work the way, modeling things more closely to the way that things actually happen, is most messages, they're received and are either immediately delivered or effectively never going to get delivered, like in terms of like the computer timescale, right? They either come straight in and go straight out, or they come straight in and I have a transient failure and they're probably going to sit there for like at least 15 minutes, right? It's a typical exponential back-off first increment, right? So 50 minutes is a really long time. So it doesn't make sense for us to receive a message, write it to disk, free things up, and then realize that we need to deliver the message and read it back in from disk and then try and send it out. It's just crazy. So we just receive the message. We'll keep the message in RAM, as long as it's not too big. I'll get to that a bit more later. We write it because we have to, and then we go and deliver it, but we deliver it out of RAM, and when we're done, we unlink it. So that's something we do there, and that works really well for us. What else? I'm sort of jumping backwards and forwards a little bit on some of my topics in here. So what we have actually works well when things are working well. Things can come and get you in unexpected ways. So in unusual circumstances, and I got a few listed up here, things sure can be fun. It depends on how people have configured the system. So there's some obvious typos that one can make. Like maybe I've put like just totally the wrong number of threads in a thread pool. Those are the simple ones. Those are easy to find. The ones that are more fun are things that are really outside of your control. So, or at least outside of my control. So I've got some notes here that you can't see that I'm reading here. So we have one of the things that can happen is you can have a deliverability snafu that causes your outbound traffic for a particular domain just to not be accepted anymore. And what happens then is we just go re-queue it, and we'll try it again later. And we have some mechanisms in place. I mentioned that we keep it in RAM. When we get a transient failure, we typically will say, like, well, screw that. There's no point keeping it in RAM. 15 minutes is a long time. We can go read it back in later on. In some circumstances, we can give up on a domain because it just looks like it's not going to happen. So what we'll do is we'll transiently fail everything that we've got for that guy. So we'll go throw away all the stuff from memory. But one of the other things that happens when we do a transient failure is we go log that, right? Because it's an interesting thing that you guys want to see. Like, I had a whole transient failure problem. So we have like some opposing forces going on. Our default logging says we should just go log that line and throw away the message from RAM. But some of our customers have custom logging turned on, where they're like, I really want to log this header out of my message. So we have this thing where we're trying to get them out of RAM, but they're pulling them back in again. And there's some interesting pressures going on because the API they use says, I really need this header. The API is like, OK, well, I'll just go read it back in because I haven't got it in memory. I'm going to pull it back in and pull it back out. So we have this I should add, there's another module that you can configure. I mentioned that paying the cost of running it to disk really sucks from our perspective because most of the time it just goes straight through. We allow you to configure it so that you don't have to write it to disk immediately. So it's technically in violation of the SMTP spec. We have these strong warnings that say, you can use it this way, but you are responsible for handling these cases. Like if the power's interrupted, like you have to take these certain steps to go purge things out or otherwise tie things back into another system. So if you've got one of those configurations turned on, we may not actually write the message until we've had a certain number of transient failures. So there can be an opposing force where we've crossed that threshold, so we've gotten rid of it, but getting rid of it means we have to write it out. But then your logging wants to pull it back in. So like there's all these weird cases where you can end up having a whole bunch of I/O torture going on because of the way that somebody configured it. So when these things come in, like we look at the ticket and we're like, oh, I bet they've got a custom logger in there that's logging a header, right? So there are some other options you can turn on to mitigate that. So there's like, and this is one of the challenges as a software vendor, especially for something like email, where the deliverability patterns and the sensitivity of those systems is such a, if we want to change a behavior, we want to be really careful about how we change it, because that can totally change somebody's sending profile by accident. So we added a knob that allowed you to control whether we do transient failures in the way that we've always done them, or whether there's like this alternate asynchronous path to go process them. And the cost you pay for doing that is you can't see some of the reception time data on some cases. So, the outbound connection data in some cases. So you can turn that on, but you have to know that you want to turn it on because we didn't want to change the default because we didn't want to piss off the other customers where it was working fine. So, there's, those things are painful, and when we find those pain points, we put in some code to try and fix it, but you have to go turn it on. So we add a knob and a way to get around it. But I have a note here about an exponential backoff standing wave. So you can have a confluence of things going wrong here too. So typically when you get a transient failure in SMTP, you'll go to the next retry interval. And SMTP tends to be an exponential backoff. So I'll try again in 15 minutes. If that doesn't work, it'll be another 30 minutes. If that doesn't work, another hour or something like that, right? There are some cases in some architectures. So it's not necessarily just our piece that's the problem point here, but so say we're having trouble getting mail out one end of the system and we have a transient failure. We'll requeue in 15 minutes time. Say there's another part of the system that wants to go send messages, say every 15 minutes, and if there's some kind of issue there, it may also have an exponential backoff. So in some circumstances, if you have a really acute problem, you can end up with a lot of back pressure on the momentum instance, and we'll be busily trying to fight for IOPS to go manage the logging and recording the data that you wanted to, and we'll requeue things for 15 minutes time. Maybe in that period, we're unable to receive as many of those messages from the other side, so it goes and requeues them internally for 15 minutes time. So then in 15 minutes, we're trying to do the same thing, so's the other guy, and so we end up with like this tremendous set of like oscillating pressure going on in the system, right? So it's not something that we can necessarily manage directly in the system, but it is one of the effects that we can see. It's just an interesting thing. There's another example of that I could get into a bit later on, but I don't want to keep going on and on and on about that. So one of the other things that's awesome about email is that people love to send other people things, right? So actually, I haven't seen this happen in a while, but a few years ago, it was fairly common for your non-technical family member to say, oh, look at this, I found this brilliant video, and attach it to an email and then send it to 100 people. So I mentioned that we keep messages in memory. So it kind of sucks to have like 100 times 10 meg in there. And that's just one person with their friends, right? So if you sort of you scale that up to sort of a bigger system with more people, with more friends and more movies, then that's quite a lot of memory just to have for the same MPEG or whatever. So what we do is we have a large message threshold. So if your message is bigger than 128K or whatever value you set it to, we'll say, well, screw that, it's too big. We're going to use an alternate reception path for that. We'll stream it to disk as we receive it. And when we deliver, we'll stream it out as well. We won't hold that in memory. So we say we're gonna eat it on this one, right? It's an outlier from our perspective. So we'll have this alternate path. That way we can efficiently manage the resources. It may not move through the system as fast as a small message, but it wouldn't have moved through as fast anyway. So we have that alternate path. Now, one of the interesting optimizations that we made for that is I mentioned policy is fantastic. So like in our default code path, we don't look in the message because we have no need to. But our customers tend to want to do that. Like, there's probably something in the message that they're really interested in looking at to go figure out what they want to do with it. So it's very likely that for a given message, someone's going to want to actually go look at it, maybe do a MIME parse. Some of the policies are like, especially if it's got a 100 meg or a 10 meg attachment on it, maybe they want to block that. So they have to go do a MIME parse on that message. So rather than put it all on disk and then go back and MIME parse it, so rather than write it all out and read it back in again to parse it and maintain that state, we parse it as we receive it. So we keep information on where those MIME parts are so that it's much faster for us to actually go pull out or reference the parts that are important. So we found that quite effective. Sadly, I feel like such a cop-out here. I don't have numbers for this because we did a bunch of this a while ago, and it's sort of like recounting some stories here. So I know you guys really love numbers and things. I don't have too many of those in here. Just that it definitely made a big difference for us. I can't remember how much. So I hope you bear with me on that one. Actually, while talking about doing some optimizations on to handle those interesting cases for MIME. I mentioned earlier that SMTP, it's line-based, and you have to search around for the end of the message. So we ran a profiler to go figure out, like, how are we doing? So we ran a profiler, and our profiler showed us that we had this function being called right at the top of the profile, find EOM or find EOL. And those functions are looking for either the end of a line, because we don't fgets on these things, right? We read things into a buffer and we go figure out where the end of the line was. So we have code that does that. We also have code that tries to find the end of the message, the crlf.crlf. We spend a really huge amount of time dealing with that because guess what? We have to do that a lot for every single message, and messages aren't just like one or two lines; they're like a whole bunch of lines, and then you got the end of the message. So we looked at it a bit, and with a little bit of idle playing around with some C code, we're like, can we make this go faster? And we tweaked a few things, and it didn't seem to make much of a difference with the C code that we had. And we thought, like, is that it? Is that all we can do? But then we hired someone that was actually something of a machine code ninja, and we said, this is the top thing on our profile. What can we do about it? He's like, let me take a look. So this is one of the things where I do actually have some numbers. So what he did was he tried a couple of things where rather than just like a really naive strustra type thing, looking for a /r/n in there, there's a couple of simple optimizations you can make to that algorithm above the naive approach where you search for just the /n and then sort of look either side to figure out whether it looks like the CRLF or not. So that red line is like the really naive strustra thing where you're looking for a /r/n. And then the x-axis here is how long the buffer is that you're looking in. And then the y-axis is how long it takes. So maybe not surprising, the bigger the string before you have the end of the line, the longer it takes to find it. using a slightly more intelligent algorithm, using memchar to look either side, we get that green line, which is like a better line. And then these two down the bottom that are really, really shallow, these are using SSE extensions. So they're like uber optimized. So he looked at the problem and he came up with like a logic map. And if you model the byte sequence, you can put them into these SIMD registers and do some SSE operations to compare. And anyway, it's awesome and it's really technical, but it has like a fantastically shallower profile on there. So this is like a 90% difference, right? In some of the larger cases, like 16K is a 90% improvement. So we actually saw an overall improvement there of 30%, right, for the systemic performance, which is fantastic. What was actually also interesting is SSE2 performed better than SSE 4.2. It has better pipelining for this particular use case. So like the new stuff, not so good. Like the slightly newer stuff was better. So that's an example of like a micro optimization, but it's like this is like one of the probably the only area now that we have assembly code. Oh, we have some lock stuff, but we have some assembly code that does this, and it's like a fantastic investment that we made into that. It's awesome. Not really a big picture thing, but it was definitely an awesome thing. So. Moving on then. So another lesson we learned, network and evented I/O. A lot of folks are already hot for the event-based model. I've talked a bit about this already. You can get a much higher level of concurrency with an evented system compared to, say, a traditional fork exec model or even a threaded model, because you can have a much lower per session overhead, right? Much smaller amount of RAM. You can fit much more of those things into the system. The challenge, of course, is that building it in C, as God intended, can be something of a challenge, right? Because the bigger the system that you're building, the more complex that is, and C doesn't really lend itself. It's not Node, right? Node has closures up the wazoo, so you can actually write some nice terse code. You can probably fit a good chunk of logic on screen, and it's fantastic. Some of the equivalent stuff in C, you may have like a bunch of boilerplate, or maybe you've got like a big case statement with a big state machine with switches and cases and go-tos and stuff in it. You don't have to write it that way, but those things tend to happen that way because you tend to be focused on performance, so you tend to write it that way to get the most out of that language. So complex and harder to maintain, but a fantastic win for us. So like it's one that we don't regret. Tied into this, we have this concept of a listener, and if you're familiar with Node, you can the logical equivalent is you create your I keep thinking of the HTTP example. That's a listener. You create your HTTP server and you have a factory method. So our listener stuff, maybe not very astonishingly, works in a similar fashion. You register a callback, and every time something accepts, it runs your callback, and then you set up your state machine and go execute that. So that's how that bit works. So one of the interesting things comes into play when you start putting policy in there. So I mentioned earlier that RBLs are like a really widespread first line of defense for people operating a receiving system. RBLs are typically DNS lookups, right? So you go take the IP address, flip it around, put the right zone name on the end, and go look that up. And if you get the right bit pattern coming back, you know that they're on the list, and you probably want to go reject those. So we don't use the system resolver for that. We use a modified version of ARES, and that's integrated into our event loop. So we'll get a dispatch into our listener callback. We'll figure out that through the policy stuff, we'll figure out that we want to do a DNS lookup. So we'll go queue that stuff up, and we'll just put that session on hold and go do some work on something else while we wait for the DNS lookup to resume, to complete. Then we can come back in and carry on from where we left off. And now we have the DNS results, and we can say, oh, they're on the list, so we want to turn them away. And that works well. In fact, it performed like a champ. So in all the testing that we had, it was fantastic. So we shipped it, and that worked for everyone until one day we deployed it at what we call a carrier class customer in North America, who I can't identify. They have a domain, and they have many mailboxes on that domain, and lots of people send to that domain. And we underestimated the load that they were getting. Does anyone want to sort of hazard a guess as to how we underestimated there? Like what? No? Any thoughts? All right. Well, I'll move on then. Basically, we couldn't keep up with the connection load. The rate of connections attempting to be established into that network was tremendous. Like we completely underestimated. Like in the lab, we have a tool we call the shit kicker, right? Like we built that tool to go stress the system so that we can crank up the load and try and make things break. So even with our shit kicker tool, like we couldn't model the same sort of load. So we turned it on, and it's turning away 1,000 connections per second because they're all RBL hits. But the throughput, the reception throughput went through the floor. Like it was nowhere near the 1 million that we said we could do. So we're like, oh, we got this covered. This is easy. We have this module that reads an RBL DNSD dump file and just loads the zone into memory. That way we can cut out that whole DNS lookup thing. We just do an in-memory lookup, and we can tell you the answer straight away. So we turned that on, and we were turning away 2,500 connections a second, but it still wasn't good enough. And so we were like, wow, like this is pretty brutal. There's like all these people that are trying to spam into this single domain across these various boxes. This is on one box, by the way, right? So. And they had more than one box in their architecture, and I can't tell you how many. So that like each box is got this tremendous crushing load coming in. So what was happening was we were spending so much time processing these accepts that our scheduler couldn't actually get to dispatching any of the actual traffic stuff that was going on. So we don't prioritize between those different classes of events, right? So it was just like a huge load. So the lesson that we learned was maybe we should do that bit in a different thread. So, just kind of like just I don't know. Event-based is the one true way, except when it's not. So what we did was we tweaked our stuff so that we could actually run the accept processing portion of that policy in an alternate thread. And in that guy, we did the RBL lookups, and then lo and behold, we could turn away 8,000 connection attempts a second. And we still had our 1 million messages an hour throughput in there. So, that was sort of like a surprising result, but in some ways not really surprising, right? But sort of the things that we'd seen and the things that we'd read led us to believe that event-based model was all we needed, but actually it turned out it wasn't. And what was actually really interesting in this case was that I say simply needs threads, and we ran it in a thread pool. What we found was that we only needed one thread extra for this. We could put 2 in there. It had no real material difference in how many of these were going on. It was just the difference was that one extra thread running on that on a different core, and then voila, we've got our system performance back again. So, sort of an interesting result. So another thing here. Yes, so this is another interesting thing. So how many of you have read this CEDAR paper? Cool, okay, so a few of you. So this paper, and this is actually quite a long thesis by this guy, and I haven't written his name down here, and it's my bad. It has this really long thesis on that examines these different server architectures and how managing the load as it goes through those things is really important to maintaining a consistent level and quality of service through the system. So like the sort of untrue hand wave summary of that thing is that if you've modeled your service as a state machine, what you do is you just basically put like a managed queue in between each stage of that state machine, right? And then you can control the throughput as things move between those different states. And that gives you a good deal of management control over messages as they move through your system. So we actually didn't model our stuff on that paper. This is just something that we arrived at independently. We've arrived at a similar architecture independently, but actually not exactly the same. So our thread pool model actually has a lot of similarities, right? So rather than having explicit, I've moved to the next state, it goes into this queue, we actually have, oh, I need to do this thing, I put it in this queue. And then when the queues are done, we reschedule and then carry on. So there's actually one critical difference between those two. I know they're not supposed to be the same, but they're very similar. There's one very critical difference between those architectures, and I wonder if anyone here has some thoughts on what that might be. And I don't expect you to, because I've been sort of talking at a high level. Any ideas? No. Okay. So the big difference is when I'm done with my stuff in the thread pool, I don't have any queue control for things when we reschedule them again. So say, well, here's like the first example. I've just started the server up. One of the things we do on startup is look through the spool to go see what mail we've got. So we have to go crawl through, find all the mail in the spool, and then we go queue jobs to go read in the metadata and then put that into the mail queue data structures. So the way that works in our system is we go read it in. Once we've read it in, we have to switch to the scheduler to go put it into the mail queue data structure. And so once we start it up, we can be receiving incoming mail. But if we have a lot of mail in the spool, we can be spending a lot of time just pulling in these messages from the spool. And it's great because we do need to do that. But the fact of the matter is that it's probably not going to go anywhere anytime soon, because the mail that was going to go somewhere, we already delivered it, right? This is probably that. This is the stuff that sits around in the system. So we can build up a whole huge backlog of these messages that we've spooled in, and we can spend all our time just pulling those in off that queue, putting them into the mail queues, but never actually dispatching the stuff to either send the legitimate mail out of that or to receive the new mail out of that. So what we needed to do is we needed to add basically a rate control over how fast those things are pulled in off the spooling queue before we go put it into our main delivery queues. So we also, and this actually ties back to the previous thing, when we added that accept processing, we actually had to add a similar break in there as well, because you can be turning over, we've got 8,000 of those things a second being accepted. If they're legitimate connections, that's 8,000 of those that we could be pushing onto the scheduler, and actually we arrive at the same sort of problem that we had in the first place, which is all these accepts are happening and we're not actually pushing any mail through the system. So we had to add another rate control there as well. So we're just like, how many we do in a tick? It's not rocket science, right? You just say, oh yeah, we'll do like 100 a tick. That's probably good enough, right? But we give you a knob so you can actually tune that either way to make that fit. So it's sort of unexpected, but a necessary aspect that we had to put into our architecture. I have another lesson here. How are we doing on time? It's 2:18. How much time we got left? Is it like 10 minutes? But okay. So we have another couple of features. So another thing that can really bite you in the ass is features interacting in ways that you didn't expect. How many of you are familiar with mod backhand? A bunch. Okay, whack-a-mole. That's actually the one I really meant. I know at least one of you is. So we have this clustering feature in our product that is a bit sort of whack-a-mole-y in its nature for good reason. Thanks, Theo. The idea is that you can run multiple nodes. And you can say, I have this pool of IP addresses, and I want to run SMTP service for this pool of IP addresses. And if one of my nodes goes down, I want some of the other nodes to go take up those IPs so we can maintain service for those IPs. And when the down node comes back up again, we'll move the IPs around. You can preference them, but we'll redistribute the IPs, and any mail that's queued to go out on those IPs moves to that node internally. We have this message move thing internally. So yeah, that's pretty cool. We have this other feature that we launched fairly recently called adaptive delivery. And what this feature does is it will dynamically tune shaping parameters in response to SMTP responses. So if it sees something that looks like you're sending too fast, it will auto-tune you down to make you go send slower again. There's also some stuff in there where it looks like, hey, we've blocked you because you're doing something really bad. Go call our support line. We'll actually suspend delivery for that domain. So that's pretty cool. That sort of takes some of the tedious manual part of deliverability management out of the equation. So that's cool. We also have these things are sort of activated by binding a message to an IP. So there's part of our policy where you can say, take this message and put it on this binding, and you can give it a name. You can also group bindings. So you could have my transactional binding group, and it could comprise of like a handful of IP addresses, which is great. So you can say, bind it to the transactional group. What will happen is it's DuraVip aware. So if that IP is on the box, fantastic. It'll go get queued, and we'll deliver it out of that box. If that IP got moved to another node, because maybe you're just injecting across them all, it will go internally, move that message to the right node, and then it will leave the system on the right node. Right? This is fantastically cool features. So the feature interaction part comes in where adaptive delivery suspends one of those bindings. No problem. We already thought of this, right? Because we handle this. The binding gets suspended on this node. So what we'll do is another binding somewhere else in the cluster will serve that IP. So we'll just move it to the node that has it, and we're good. Job done. So when it gets to the other node has a deliverability problem, and adaptive delivery suspended the IP. So on this other node, it's like, well, yeah, I would do it, but my IP suspended. So I'm gonna give it to somebody else in the cluster to do it. So it moves back to the other node, and the other node's like, damn, well, I don't have any IPs for that, so I'm just going to give it to another node in the cluster to do. So then what ends up happening, and this is, I'm smiling now, but it was really quite a miserable experience. What ends up happening is the mail really looks busy moving mail around, but there isn't much going out, right? Because it's just moving around in the cluster, right? And the more nodes you have, like who knows where it's going? It could be going up and down and around, and you're killing your disks because you've got all this mail coming in. You have to keep writing the frickin' thing to disk and then unlinking it and putting it back in, and it was just like a real miserable interaction for us. So what we actually missed there was sharing the information about whether adaptive had suspended a binding or not. So, it's such a simple a simple mistake to make. But anyway, we added in the ability to actually see the other nodes had suspended it, and now we have so much better logic, so we don't waste our time moving things around. So. It was a fun time. It wasn't a fun time. It was a very stressful time. So anyway, so a lot of those things were born out of quite intense pain, and I think I've done perhaps too good a job of not conveying just how painful those were. Part of that may be because I wasn't literally the guy who was there on the console for a lot of those things, but I was very close to that part of the escalation path, so I have like a lot of empathy for the folks that were. So just to sort of wrap things up, hopefully you guys already have a lot of these things close to your heart already. What we found is to have a good architecture in a system, you need to understand what it is that what you're trying to do. And in the case of a software vendor, we need to understand what you're trying to do, not what we're trying to do, and make the system model that in an effective way, so you can actually get things done, but also get it done in a way that allows you to get your things done. That's a really fluffy kind of statement, but so you can come up with a really good idea until you've actually tried it out and measured it. You don't know if it really is the good idea, right? It may seem like a good idea, but you need to try it. You need to measure it. You may see something that looks like it's a bad idea, but you just don't know. So, like, go in there, look at it, measure it, and see if it needs fixing, and then fix it. And as part of that, you need to allow folks to actually get in there and see those things when they go wrong. And this is something that's sort of core to what we build. I haven't really shown it at all on here because I don't have anything to show on here. But but we have this console channel where you can go in and you can ask the system, like, how are my thread pools doing? Because we have all this instrumentation that says, like, here's how long I'm spending doing this particular type of job in this thread pool. Well, like, here's my average wall clock time. And here's my queue length. So you can actually go look at those things and instrument those and figure out what's going on. So we've put in quite a good amount of observability into the system. We haven't built dtrace into it. You can use dtrace with it, but because we run on Linux as well, like we can't just default to assuming everyone's got dtrace. But not only the observability, but also the operability. So we have a lot of controls where you can go in and say, like, crap, like I just want to suspend this thing, or I want to go change this knob now because I've realized that that's really what I want to do. So we actually have the ability to go change those things at runtime without restarting the whole process, which is also a huge time investment to make that work. But again, it really works out for us. And by extension, how many of you read Theo's blog on a semi-regular basis? A few. So he had a blog post with a really awkward title, which was, I think you pronounce it Yawahusti. But basically, it's an acronym that says, you will always have users smarter than you, right? So I don't profess to be smarter at getting my stuff to operate on your systems than your awesome ops teams, right? So I want to make sure that we give a good amount of control for you guys to actually go in there, like, poke those things, like, oh, this isn't working right. Let me go see how this is working, and let me go poke those knobs to make it work right. And that can shortcut a lot of things, because we can't go recompile the code every time we want to tweak something. We need to make that more operable. We also have ninja mode and knobs, so that we also have some, like, super advanced secret debug ninja mode things in there as well for us to get some data out. Like, just go, if you're building a system, like, build that shit in there so that, because it's going to pay off at some point. Like, there's going to be a time when someone's going to need to go in there and, like, I really need to change this parameter. Like, when we spec this thing, we've figured out this algorithm. There's this constant in there. We made it a constant, and now we realize we actually need it to be tunable. So let's make it tunable, and that's what we do. We try and put a tunable in there. We try not to second guess any of that stuff. So anyway, enough of me rambling. Are we totally out of time for questions? We've got 2 minutes? 2 1-minute questions. So does anyone have any questions for me? Maybe. All right. Really? All right. Okay, yes. Okay, yeah, so the question is how do we do throttling in an event-driven architecture? One of the ways that we do that, we have a couple of different ways, but like the easiest way for us is not only do we have an event-based scheduler, we also have a time-based scheduler. So when the scheduler goes to sleep, we can set, like, the maximum sleep interval. So we have, like, one set where the kernel's telling us about I/O. We also have an internal time heap. So we can say, like, this is triggered at this time. So when we throttle, what we do is we unsubscribe from the kernel I/O notification. We put in a timer of the right duration, and then that wakes us up, and we can carry on. So any others? We're done. Okay, thank you very much.